Introduction to Quantum Information Processing. Welcome to Lecture 2. In this lecture, we are going to see how systems involving multiple qubits work. Some broad questions that will arise are, do subsets of qubits have quantum states? And can operations be performed on subsets of qubits? Up until now, we have considered systems of a single qubit. Let's consider the case of multiple qubits. First of all, for n classical bits, there are 2 to the n possible values, and a probabilistic state has a probability associated with every n-bit string. So the state is a 2 to the n dimensional probability vector. For n quantum bits, there are 2 to the n amplitudes, and the state is a 2 to the n dimensional vector of length 1, a unit vector. The set of all valid probability vectors is a simplex, which is illustrated for the case of 3 dimensions as a triangular region. The set of all valid quantum state vectors is a hypersphere, which is all points of distance 1 from the origin. There are 2 to the n computational basis states, denoted as n-bit strings within kets. As with single qubits, what's important is the operations that can be performed on them. We'll consider unitary operations and measurements. Unitary operations are 2 to the n by 2 to the n unitary matrices acting on 2 to the n dimensional vectors. Measurements have 2 to the n outcomes corresponding to the 2 to the n computational basis states. Each basis state outcome occurs with probability the absolute value squared of its amplitude. So far, everything is the same as for qubits, except with 2 to the n dimensions instead of 2 dimensions. But there's more to it than that. There is structure among subsystems. First, let's consider how subsystems work for the case of a classical n-bit system. It can be viewed as one system, shown here as a rather bloated USB memory stick. But we can also view the n-bit system as n separate 1-bit systems. Let's explore that. We can consider the state of every subset of the n bits. We have a probability vector for the entire system. For 3 bits, it would be this 8-dimensional vector. What's the state of the first bit? The probability that the first bit is 0 is the sum of the first 4 probabilities. That is, all cases where the first bit is 0. And the probability that it's 1 is the sum of the last 4 probabilities. In this manner, we can deduce the probability vector for the first bit. Similarly, we can deduce the probability vector for any subset of the bits. In the language of probability theory, what we're doing is taking marginal distributions of a multivariate distribution. Also, an operation can act on a subset of the bits. For example, if there are 3 bits, it makes sense to apply an operation to the first bit. For example, think of how applying a NOT operation to the first bit affects the 8-dimensional probability vector. And operations can be similarly localized to various other subsets. Now, consider subsystems in the context of an n-qubit system. It can also be viewed as one system, shown as a bloated quantum USB memory. but it can also be viewed as n separate 1-qubit systems. Can we consider the state of every subset of the n qubits? For 3 qubits, there is an 8-dimensional amplitude vector. What's the state of the first qubit? We could try summing the first 4 and the last 4 amplitudes, as we did for probabilities, but that doesn't work. In fact, it's not too hard to even come up with the state where both of these sums are 0. And having a qubit where both of its amplitudes are 0 makes no sense. Can we do something else? It turns out that states of subsystems are a bit tricky. We will be able to better address this matter later on in the course when we consider mixed states. For now, it suffices to be aware that in some cases, there does not exist an amplitude vector for a subsystem. In this sense, the larger system must be considered for a state to make sense. Now, let's consider applying operations to subsets of the qubits. If there are 3 qubits, does it make sense for a unitary operations scope to be the first qubit? The fact that the first qubit might not even have a state vector suggests that this is not an entirely trivial matter. But it turns out that there is a fairly straightforward way to make sense of operations whose scope is limited to a subset of the qubits, and we'll see how to do this shortly. If Alice possesses the first qubit and Bob the last 2 qubits, then it turns out that Alice can perform an operation on her qubit without touching Bob's qubits. And we'll see that this works for other subsets too. By the way, this kind of data flow diagram is called a quantum circuit. There are 2 ways of viewing a quantum circuit. One way is that the lines are wires and the qubits flow along the wires from left to right and are transformed when they pass through the boxes, which are called the gates. Another way of viewing a quantum circuit is that the qubits stay put, and the horizontal axis only represents time. Quantum circuits are a useful way of representing quantum information processes, and you'll be seeing a lot of them. Let's get back to the issue of quantum states of subsystems. Remember that I said multi-qubit amplitude vectors do not always have meaningful amplitude vectors for their subsystems. Suppose we build quantum states bottom up, starting with the states of the subsystems. For example, consider 2 qubits in these specific states, with amplitudes alpha 0 and alpha 1 for the first qubit, and beta 0 and beta 1 for the second qubit. We can choose to consider these 2 qubits as one system, a 2-qubit system, whose state is a 4-dimensional vector. What is the 4-dimensional vector? It's the tensor product of the 2 2-dimensional vectors. An intuitive way of thinking about this tensor product is to kind of expand the product of the 2 superpositions. The product of alpha 0 and beta 0 is the amplitude associated with ket 0, 0. The product of alpha 0 and beta 1 is the amplitude associated with ket 0, 1, etc. This is exactly analogous to what we do when we have 2 probability distributions, and we want the probabilities of the joint distribution, assuming that the 2 systems are independent. We can define this formally with a tensor product operation on the vectors. In fact, we will define the tensor product more generally than for vectors. We'll define it for arbitrary matrices, where the case where the matrices are column vectors is just a special case of that. The tensor product of 2 matrices, also called the Kronecker product, is defined as follows. The matrices can be of arbitrary dimensions. For each entry of the first matrix, take that entry and multiply every entry of the second matrix by it. That is one of the blocks of the tensor product. For example, A11 times the whole matrix B is one m by n block. Then A12 times the whole matrix B is another m by n block, and so on. If A is a k by L matrix and B is an m by n matrix, then their tensor product is a km by Ln matrix. Suppose we're given a 2-qubit state, a 4-dimensional amplitude vector. Can we deduce the states of the individual qubits? For this example, it's not hard to see that it should be a uniform superposition for each qubit, a tensor product of 2 ket plus states. What about for these 3 cases? You can pause the video to think about this. Okay, for the next state, we can get those 2 minus signs in the right place by taking the tensor product of 2 ket minus states. The next one, we can think about it a little, and we can get this. What about the last one? If you tried to work it out, you probably realized that there is no solution. The last one cannot be expressed as a tensor product. It's a fairly straightforward exercise to prove this. It's an example of an entangled state. We'll see that these 2 qubits in such a state can behave in interesting ways. It's especially interesting when the 2 qubits are physically in separate locations. Say one qubit is in Alice's lab and the other qubit is in Bob's lab. Now is a good time to discuss the matter of global phases. You may have noticed that the aforementioned factorizations are not unique. For the first example, the factorization can be in terms of 2 ket plus states, or 2 states with minus signs for each amplitude. So, what's the difference between the state ket 0 plus ket 1 and the state minus ket 0 minus ket 1? As vectors, they are not orthogonal, but they are certainly different. The angle between them is 180 degrees. Can we distinguish between them? Suppose you're given a qubit in one of these states, but not told which one. Is there some measurement procedure for determining which one it is? Of course, you could always ignore the qubit and make a random guess. Then you'd be right 50% of the time. But can you apply some measurement procedure that enables you to do any better than random guessing? The answer is no. For any measurement in any basis, the outcome probabilities will be identical for both states. Since there's no way of distinguishing between the states, we regard them as equivalent. And based on this, we define an equivalence relation on amplitude vectors. We say that 2 vectors are equivalent if one of them differs from the other by multiplying by a complex number with magnitude 1. This number can be -1 or any complex number of the form e to the I theta for any real number theta. The factor e to the I theta is called a global phase. Global because it's applied to all the terms in the superposition. Here's an exercise if you'd like to get used to this concept. Now, let's consider the matter of the scope of unitary operations. Suppose that there are 2 qubits and we want to apply a 1-qubit unitary to the second qubit and do nothing to the first qubit. U is a 2x2 matrix. Is there a 4x4 matrix acting on the 2-qubit system that expresses this? If the individual qubits happen to be in computational basis states, then it's reasonable that the first state does not change and the second state is acted upon by U like so. This makes intuitive sense. Now, if we have a 4x4 unitary matrix whose effect on the basis states is this, then by linearity, it must be this 4x4 matrix. This is what we take as the definition of doing nothing to the first qubit and applying U to the second qubit. Notice that this operation can be applied to the 2-qubit system in any state, even in an entangled state. Whatever the state is, it's a 4-dimensional vector, and it makes sense to multiply it by this 4x4 matrix. Interestingly, this 4x4 matrix is the tensor product of the identity matrix I, the 2x2 identity matrix, with U. Here's a question to consider. What if we want to apply U to the first qubit and do nothing to the second qubit? By a similar approach, you can work out what the resulting 4x4 matrix is. We've discussed localized 1-qubit unitaries in 2-qubit systems. Clearly, this generalizes naturally to more qubits. For example, when there are n plus m qubits, and U is applied to the last m qubits, think about what the form of the 2 to the n plus m by 2 to the n plus m matrix would be. Also, when V is applied to the first n qubits. Furthermore, if U and V act on separate qubits, it's natural to expect the two operations to commute. That is, their net effect is the same regardless of which one is applied first. It's actually not too hard to prove this, and I suggest it as an exercise. To prove it, it's useful to use the following lemma about the tensor product. A final comment: if U and V overlap, then in general, the operations will not commute. Now I'd like to show you something called a controlled Ugate, where U can be any unitary operation. Let U be a 2x2 unitary matrix. The controlled Ugate is denoted like this, with U drawn as acting on a target qubit, but with a wire coming out from a control qubit towards. This gate has the following effect on the 4 computational basis states. If the control qubit is in state ket 0, then nothing happens. And if the control qubit is in state ket 1, then U gets applied to the target qubit. This is looking similar to the case where U is applied to the second qubit, except that it appears to only get applied when the control qubit is in state ket 1. By linearity, we can deduce from this the 4x4 matrix of the controlled Ugate. Notice that it's like the matrix for applying U to the second qubit, except that the first block is identity rather than a copy of U. Here's a question to consider. Can the control qubit change state by such an operation? What does your intuition say? A spoiler alert. This question will be answered during this lecture. So, if you want to try to figure this out yourself, you should definitely pause the video. Let's consider a specific controlled Ugate for the case where U is the poly X, the NOT gate. There is special notation for this gate. To understand where this notation comes from, consider what happens when the inputs are in computational basis states. Let the inputs be ket A and ket B, where A and B are bits, that is, each is 0 or 1. For these input states, the second qubit gets negated if and only if the first qubit is in state ket 1. Nothing happens when the first qubit is in state ket 0. This is equivalent to saying that the output bits are ket A and ket of A XOR B, where XOR means exclusive OR. If you haven't seen the exclusive OR operation before, here's a table of its values. It's like a logical OR, except that the value is 1 if and only if one of the two input bits are 1, but not both. The ordinary logical OR of 2 bits is also 1 in the case where both bits are 1. Another equivalent way of thinking about the XOR operation is that it is the sum of the 2 bits in modulo 2 arithmetic. The way that the symbol for XOR is embedded into the gate symbol is kind of suggestive of what it does. Of course, this discussion is for the case where the inputs are computational basis states, ket A and ket B. When the input state is some arbitrary 4-dimensional state vector, the effect of the control NOT gate is defined as applying this 4x4 matrix to the state vector. It does what it does, independent of any intuitive picture that's based on the very special case of computational basis states. Remember, I asked the question about controlled Ugates. Can the state of the control qubit change? What did you decide? You can pause the video if you'd like to think about this further. Well, the answer might surprise you. For some input states to the controlled NOT gate, the control qubit actually changes. Remember the plus state and the minus state. Suppose the input control qubit is in state plus and the input target qubit is minus. Then it can be verified by calculation that the output qubits will both be in the minus state. So for this input state, the control qubit changes from the plus state to the minus state. And recall that, as we saw in the first lecture, the plus state and the minus state really are different states. They're orthogonal and perfectly distinguishable. The controlled NOT, abbreviated as C0, has many interesting properties. Another property concerns the simulation of other controlled U gates for different unitary operations U other than the X gate. Suppose that we have the capability of performing a C0 gate plus all 1-qubit unitary operations, and that's all. Then, can we construct a circuit with these gates for implementing other controlled U gates? Let's start by considering the example of a controlled rotation gate for some rotation angle theta. How do we do this? Well, we can guess a few simple forms that the circuit might take. Consider a quantum circuit of this form. Do there exist unitaries V and W such that this circuit simulates the controlled rotation? The answer is yes, and I leave this as an exercise. A hint is to consider setting V and W to rotation matrices with carefully chosen angles such that the net effect of the circuit is the controlled rotation by theta. This exercise is a good starting point towards a more challenging question, which is to simulate a controlled U for an arbitrary unitary U, not necessarily a rotation. If you take on this question, then I suggest that you begin by considering the case where U has determinant 1. Okay, let's end the lecture on this.